Hello, today we will be starting with mass transfer operations, a new topic in chemical engineering. So subtopics would be the importance of mass transfer and the different unit operations involved when you contact two or more different phases. Let's see the importance of mass transfer. Mass transfer from a chemical process point of view, any chemical process consists raw material, purification or directly taken to the reactor. The reaction is carried out, followed by the separation. So depending on the type of the reaction and the reactor design, we would be having the product present along with the byproducts which are to be separated. So purity of the product initially depends on the type of the reactor and then on the separation process. So finally, it's the separation process which helps us to recover of the product with the required purity. So let's see how separation mass transfer plays an important role. Mass transfer from the gate point of view, normally we have about 5 to 6 questions on an average. It may be more than that, but 5 to 6 questions on an average can be considered. So it's an important chapter not only from the chemical engineering process point of view, but also scoring in the entrance exam. So the importance of mass transfer, as we know, is mass transfer is the transfer of the solute taking place between the two or more phases. So for any chemical process, what we have is unit operation and unit process. Unit process is where the chemical change actually takes into account. So it's the reactor where the unit process occurs, that is A converting to B. It's the chemical change. Whereas the unit operation is where there is physical change involved, that is the compositions of the solution or the mixture gets changed from concentrated to dilute or dilute to concentrated, or transfer of one solute from one phase to the other phase, or it may be just the separation of the components. So let's take a different example, like we have distillation column in a process. So what does distillation column do? Initially we may be having a homogeneous liquid feed. This homogeneous liquid feed is what is through the heat input gets separated into two, that is liquid and vapor. Vapor on condensation may lead to another liquid, this is L1 and L2. L1 and L2 both may be of some purity. So in that way, what we are doing is, we have led to the separation of the phases and then getting the compositions different. So that is because of the mass transfer from one phase to the another phase, we are able to get L1 and L2 of some purity. So now any transfer involves two types of movement. It may be a bulk movement or it may be a diffusion movement. Bulk movement, as we know, is when water flows through a pipe, it flows because of the delta P, that is the pressure difference. So that is what is the bulk movement. Whereas the diffusion movement is, if you have a pool of water on the water surface, air is blowing up. So the water from the pool surface tends to evaporate depending on the concentration difference from the pool surface to the air. This is pool, air. So water tends to evaporate from the surface of the pool to the air. So that is the diffusive movement of the water molecules from the region of higher concentration to region of lower concentration, until when this diffusion occurs, their equilibrium is achieved. So let's see how this different phases involved characterize different unit operations. So we have now three states of matter, that is solid, liquid and gas. So depending on the contact between the two phases, we may be having 6 possibilities. 6 possibilities, that is gas with gas, liquid and solid. Then it comes liquid with solid as well as liquid itself, and solid with solid. So let's go one by one, classifying different unit operations involved when the contacting phases are as listed. So the revision of this part would be the mass transfer. Importance of mass transfer basically plays an important role in the separation part of the process. Different unit operations are involved, where it may be a physical change or just separation of the substances. Separation part plays an important role. Once the reactor design is done, to get the required purity is the separation part of the process, which plays an important role, and in that the mass transfer. We have product along with the co-products or the byproducts. So the purity of the product as required can be achieved only through mass transfer of one of the components from one phase to the other phase. Now in that mass transfer we will be having bulk movement and the diffusive movement. Bulk movement is which goes through the flow, takes place in accordance with the velocity of the flow. So that is like water flowing through a pipe is due to the delta P. So that is what is bulk movement, whereas diffusive movement is something flowing because of the concentration gradient between the two phases. Water from the pool of the surface tends to evaporate to the air flowing over it because of the concentration gradient which is developed. And depending on the phases, we have 3 states of matter, gas, liquid and solid. How you contact, that would classify 6 different possibilities, and within each of the category we have different unit operations that we would be listing. So now for the first category, that is gas and gas, very few exceptions are there where we have immiscible or immiscible mixture of 2 gases, whereas normally it's the soluble mixture. 2 gases are soluble in each other, so we have a homogeneous mixture. Maybe air plus ammonia or air plus CO2. Air itself is a mixture of many gases. So as such, we don't have 2 immiscible phases normally, but still the separation is possible when we have 2 or more gases of different, chemically different, that is of different molecular weights, chemical structure is different. So if we want to separate these gases, one of the unit operation may be passed through a microporous membrane. These membranes consist of pores of different sizes. Depending on the molecular weight of each of the solute which is in the gas phase, the diffusion rate would be different. So diffusion rate is nothing but inversely proportional to the molecular weight. So depending on the molecular weight, the diffusion rate of each of the gases solute from the mixture to that of the membrane side would differ. So what the composition over here of the field, and that after passing through membrane, that is the product, would be differ. That is because of the difference in the diffusion rate. The difference in the diffusion rate is because of the difference in the molecular weight. So when it passes through the pores, it feels different resistances. Each solute molecule would feel different resistance, and hence there would be a difference in the diffusion rate. So what we have is achieved separation. Our aim is basically to separate mixture of gases. So feed is a gaseous mixture of different molecular weights of different chemical structure. Membrane is microporous. Gases of different molecular weight lead to what? Difference in the diffusion rate, and hence separation is achieved. So this may be one of the unit operation when we have gas plus gas as a mixture. Then we move forward, we go for gas and liquid mixture. For gas and liquid mixture, now there is one phase which is in the gaseous phase and another phase is liquid. So different unit operations can be characterized. It's distillation, then you may think of absorption, so distillation, the feed may be only liquid or it may be vapor plus liquid, partial vapor, partial liquid, only liquid. You provide heat to the system. Let's take the example of MEOH plus water as the feed. We have provided heat to the system, so that may be the product. This is feed. We have provided heat input, vaporized. You get the product which on condensation gives the liquid. So what we have achieved is initially we had homogeneous feed. This homogeneous feed, due to the heat input, so the temperature changes involved, it starts vaporizing depending on the heat input which we have provided. So what we have is vapor. This vapor and the feed differ in the compositions. So there is mass transfer involved from the feed to the vapor phase, and hence on condensation we get the liquid product. So this liquid product and the bottom product, so what we call this as distillate. This is the bottom product. Both differ in the compositions, hence we have achieved the separation. And there is mass transfer involved from one phase to the other phase. So in this case, methanol and water, depending on the relative volatility, methanol has a low boiling point, that is high relative volatility. So it will, vapor would be having greater composition of methanol compared to that of the water. So the distillate would be having greater purity with respect to methanol, whereas water with respect to water. We will be studying distillation more in detail later, but it's just how the mass transfer plays a role over here. Then we have absorption, which is again gas liquid operation. So in absorption, what you have is a solute present in the gas phase is absorbed in the liquid phase. The liquid phase is the solvent. Example, maybe HCl gas absorbed in water, or it may be sulfur SO3 or CO2 in some alkali solution. So basically you have two contacting phases, gas phase and the liquid phase. We have an interface. So now there is some partial pressure at the gaseous phase. This suppose may be the interface. This is the flame across which resistance will be there. So it's solute from the gas phase which is absorbed in the liquid phase. So there is mass transfer of the solute from the gaseous phase to the liquid phase. Thus we get the gaseous phase solute getting dissolved in the liquid. So the concentration changes prevail. Again it's the gaseous phase solute which is diffusing. Initially it may be through the external diffusion if it's an impure gas. So there will be external diffusion. Then reaching the interface and then diffusing into the bulk of the liquid. So what you have is a solute getting dissolved in the liquid phase through absorption from the gaseous phase, and that is because of mass transfer, because of the concentration gradient which exists, and it will stop when the equilibrium is reached. So this absorption may be physical absorption, that is just the gaseous phase solute is dissolving in the liquid, or it may be chemical absorption where the gaseous phase solute is dissolving in the bulk of the liquid and then reacting with the liquid molecule. So HCl gas getting absorbed in water would lead to HCl acid. This is characterized under physical absorption, since there is no chemical reaction involved when HCl gas is getting absorbed in water. When the sour gases like SO3 gas or CO2 gas is getting absorbed in the alkali solution, so what we have is a component A, component B, both will react. If you take SO3 and NaOH, what we have is, depending on the quantity of NaOH present, you would be having sodium sulfate or sodium bisulfate. So here we have chemical reaction taking place along with the absorption. So chemical absorption would lead to greater absorption of the solute. So when we have more of the gaseous phase solute and we want to absorb it, physical absorption would just lead to accumulation of the dissolved gas in the liquid phase, whereas chemical absorption would first absorb it and then reaction. So there would be enhanced absorption because of the chemical reaction which takes place in the bulk or in the flame. So depending on the type of absorption carried out, we would be having different products and different compositions in both the phases. So again, there is mass transfer, two phases involved, mass transfer and hence changing composition. In all of the unit operations, aim is either to separate one component from the other or change the composition of the field solution. Within absorption, we maybe have conditions like desorption. The desorption is, you have a liquid phase in which gas is dissolved. Now this liquid phase is at a higher concentration of the solute. Solute is nothing but the dissolved gas. When this liquid phase is brought in contact with a gaseous phase, the dissolved gas tends to dissolve or move from the liquid phase to the gaseous phase. So an example would be when we have air as one of the gaseous phase and water ammonia solution as the liquid phase. So ammonia tries to get dissolved from the liquid phase to the gaseous phase depending on the concentration levels. But true, the dissolved gas present in the liquid phase should have higher concentration when compared to the partial pressure of ammonia in the vapor phase. So this is reverse of the absorption and we call it as desorption. Also absorption is characterized when we have humidification and dehumidification of air. Humidification of air, what we mean is water tends to evaporate from the surrounding or the liquid phase, pool or whatever, to the air. So the partial pressure of water vapor in the air tends to increase due to the evaporation of the water. So that is what is humidification of air. Whereas dehumidification would be water vapor or the moisture from air going back to the liquid phase, that is condensing. Condensation leading to water. So the advantage is humidification is like absorption of water from liquid phase to the gaseous phase, so it's like desorption, and dehumidification is like absorption. It's the reverse in this case. So dehumidification, the moisture from the air would condense till the partial pressure of water vapor in air is equal to the vapor pressure of water at that T, that is temperature. We will be studying this operation again in detail, but the basic principle would be condensation of water vapor from air to the surrounding would happen when the partial pressure of water vapor in the air is equal to the vapor pressure of the water at that temperature. So that is what defines the dew point. So thus we have studied when we have two conducting phases of gas and liquid, they have different unit operations. Main is distillation and absorption. Within absorption we have again desorption, which is reverse transfer of the solid from liquid to the gaseous phase, and humidification, dehumidification can also be considered as the part of the absorption process. So going further, we would be having gas, solid and the contacting phases. Gas, solid, the unit operations which come under this category are adsorption, penetration, let's see what is adsorption. It's like the process you may have considered is the drying of air, which is important when you are manufacturing some pharmaceutical tablets in an environment or the facility which is to be GMP compliant, that is good manufacturing practices. So you need to have the facility where the air is highly purified and dry. So this drying of air and purification both come under this unit operations. Drying of air would be, now air has moisture, that is water vapor, along with it. So this air plus water vapor mixture is passed through a solid material called molecular sieves. These molecular sieves are basically again a microporous material. They have different attraction towards the solutes of different chemical nature. So again, it's like the gaseous solute gets adsorbed. Gaseous solute getting adsorbed on the solid phase. This adsorption may be physical adsorption or chemical adsorption. Physical adsorption takes place because of the van der Waals force of attraction between the solutes of the gaseous and the liquid phase, whereas chemical adsorption is due to the valence forces of attraction because of the valence electrons present in the solute of both the phases. So chemical adsorption is stronger compared to the physical adsorption, and this is what is made use of in most of the gas solid reactions, where the solid is a catalyst on which the gaseous phase solute gets adsorbed. That is at the active site. So active site is what is resembling the solid phase and the gaseous phase solute getting adsorbed. This is what is made use of in the chemical reactions, gas solid chemical reactions. Now here, so water vapor and air would have a different rate of attraction capacity or of getting adsorbed or getting attracted towards the molecular sieves. So water vapor has tendency to be with the molecular sieves. So finally, after having passed the moisture vapor laden air through the molecular sieves, what we get out is the dried air. So what we have occurred is mass transfer from the gaseous phase to the solid phase. That is because of the adsorption. Other solids that may have used, we have studied is activated carbon, which is normally used as a support. Silica, activated carbon. Then we have silica gel. Then we have zeolite. Which either act as the inert support or also may play a role in the gas solid chemical reaction as the catalyst. Zeolite has H plus ions, act as the source of the H plus ions, hence the acid catalyzed reactions. So within adsorption, again two contacting phases, mass transfer, and how it takes place is because of the difference in the adsorption rate. This adsorption difference is because of the chemical constituent nature of the solid phase solid as well as the gaseous phase. So physical adsorption and chemical adsorption. Chemical adsorption stronger compared to the physical adsorption. It's characterized mostly by the gas solid reaction which occurs. Example of air getting dried. Filtration, again air may have some suspended particles which are to be filtered. So this air with suspended particles pass through the filter medium. This filter medium would then lead to the purified air. So it's basically filter medium removing the suspended particles present in the air, and hence we get the purified air. This is what is made use of in HVAC system, that is heat, ventilation and air conditioning system. We first go for a filter medium of, again this would be a porous material of different pore length, pore size. So again first you would remove the coarse particles and then the fine particles, and hence you get the purified air. This is made using HEPA filters, which mostly the pharmaceutical industries and food industries make use of. HEPA stands for High Efficiency Particulate Air Filter System. So here the contacting phases and how the mass transfer plays the role. Here it's just the separation. We are not involved with the concentration to dilute or dilute to concentration. Here it's just the separation of the suspended particles from the gaseous phase. So going further, so can you guess what remains now is we have completed the three possibilities with respect to the gas phase. Now it is the liquid. So liquid with liquid. So here the possibility of immiscibility exists. We have aqueous and organic which are immiscible. can think of the examples. An aqueous phase, water definitely. Organic, maybe CCl4 or some higher alcohols which are immiscible with water, or maybe having some partial miscibility. So again there exists partial miscibility, complete miscible, or complete immiscible. Now during your lab experiments you may have carried out extraction process in the lab. So how that extraction process is carried out, we have a separating funnel in which you have L1 and L2 as the mixture, and your aim is to separate a solute from the L1 phase to the L2 phase. Now this L1 phase, so you make use of the extraction solvent, which will allow you to separate A, which is present in higher amount in L1. Extraction solvent to remove A from L1 to L2. So let's take the example of acetone water mixture, which is to be, from which the acetone is to be removed. So you want water devoid of acetone. So what you do is you make use of the extraction solvent. The extraction solvent is maybe some organic phase which will be having affinity towards the acetone, CCl4. Take the separating funnel, mix both the mixture, that is the acetone water mixture plus the CCl4 solution. Mix vigorously and allow it to stand for some time. The solute, which is the acetone, gets transferred between the two phases, and depending on its affinity towards the phases as well as the distribution coefficient or the partition distribution coefficient, you get finally more of acetone in the CCl4 because of affinity towards the organic phase. So thus the acetone gets transferred from the aqueous phase to the organic phase, and that is because of the mass transfer taking place between the two liquid phases L1 and L2, leading to the concentrated solution of acetone in the organic solid. Now again, if you are interested in recovering acetone from CCl4, you have to go for further unit operation, maybe distillation if there is a relative boiling point difference, or carry out some other reaction depending on selection of the solvent. Also involves different factors depending on the aim of the experiment. So it's basically here what you do is mix vigorously, so there is mass transfer involved, and then you allow it to separate, settling of the two phases, allowing it to reach equilibrium. So finally we get the concentrated solution of acetone in the organic phase. So this is basically what we do in the lab, and this is called as the stage-wise extraction. Extraction is basically the unit operation, and stage-wise. Why? Because we have L1 and L2 phases brought into contact and allow it to settle. So that is the one stage, or the ones when L1 and L2 are mixed vigorously and allow it to settle it. So if you carry out this many times, then there will be cascade of these stages which will finally allow it to equilibrium to be reached. Again, this operation we will be studying more detail from the design point of view as well as from the calculation point of view. So going further from liquid phase, the next part is definitely the liquid solid phase. So for the liquid solid phase, different unit operations which come under this category would be, you think filtration definitely, which we have studied before for gas solid. Then we have crystallization, filtration, similar to the gas solid operation. You have a filter medium. Suppose you have a slurry in which you have liquid plus insoluble solid. So this insoluble solid is what you want to filter it out. So you have a filter medium, some size which will allow you to separate the solid. So depending on the size of the solid particles, you select a filter medium. This slurry is then passed to the filter medium, and what you get on the filter medium is the cake, that is nothing but the solid cake, and at the outlet you get the liquid pure solution. So the unit operation is filtration. You have either liquid plus solid mixture passed to the filter medium. The solid particles get removed, get deposited on the filter cake in the form filter medium in the form of the cake, and liquid as a pure solution is obtained. So there is transfer of solute from the liquid phase to the solid phase, and hence you get the change in the composition of the liquid feed. Now this cake again may be further purified. This cake may be in contact with still some liquid material. So after filtration, always washing operation is carried out of the cake so that the cake is fully devoid of the liquid material. Depending on the end use, what's your main objective, either to make use of the liquid or use of the solid, you design the operation. Then you have the crystallization. Now this crystallization is somewhat more into use when we have solid as the product. Crystals are considered to be the purest state of matter. So when you have solid product in the form of a solid, so you have to crystallize it out from the reaction mixture. Crystals, purest state of matter. Importance of this operation: when you want solid, product is solid in nature. So from the reaction mixture, try to introduce some solvent in which solubility exists of that solid product. The condition when the solid crystallizes out would be when the supersaturation is reached. Every solid would be having some solubility in the liquid phase. So your aim is to reach that solid liquid mixture to supersaturation. And how that supersaturation is reached? It may be reached either by cooling, because most of the solutes have the solubility decreasing with decrease in temperature. Though there are few exceptions like the hydrated salts, for which the solubility increases with increase in temperature, decreases with increase in temperature, but normally this trend is followed. You decrease the temperature, solubility of the solute in the liquid decreases. So for the solvent amount, initially which was at T0 and then at T1, T1 is less than T0. Initially at T0 you had a saturated solution. Now after decreasing to T1, the saturation has further decreased, but that solute is present. So that extra amount which has made it to the supersaturation region would crystallize out. So then you get liquid solution, again liquid plus solid solution and pure solid. So this can be taken to the filtration process to recover the pure solid, and liquid plus solid, which is in technical terms called as the mother liquor, is sent back to the reactor, that is recycled, or if possible, depending on the type of solvent you have used, to go for distillation or evaporation of the liquid solvent. So basically you are interested finally in getting two phases. One is the mother liquor phase, that is liquid plus solid phase, and another is the pure solid phase. Cooling is one of the options to reach saturation. Other option is to go for vaporization of the solvent. This vaporization of the solvent would either be through heat input or through applying vacuum. So through vacuum, again it leads to adiabatic. If you just apply vacuum, the heat required for the vaporization, that is the latent heat, would be taken from the solution, and hence the solution would cool. So the third factor would be vacuum. Vaporization would lead to either through heat input or through vacuum. Through vacuum, if you are not providing any heat input, then it would lead to adiabatic cooling. So adiabatic cooling would mean you have cooling plus vaporization both together, leading to supersaturation of the solution. Again, this operation would be changed in more detail, but the basic would be how to reach the supersaturation and how the separation of the two phases occur. So coming to the last category is solid-solid category. So for the solid-solid category, the importance is you have both the phases S1 and S2, or you have a single mixture, solids of different particle sizes, and your aim is to separate all the solids depending on the particle sizes, or you want a solid of bigger particle size to be grounded or grinded to a smaller particle size. So the operations involved would be, if you want to separate particles of different sizes, then it would be sieving. So again, that will involve using similar to filter medium of different pore sizes, through which the particles would get separated according to the particle size, and this would be grinding, where the particles of a bigger size is grounded to the particle of the smaller size. Normally the diffusion in solids is difficult, very slow, and also the diffusion coefficient is dependent on the direction of the movement of the solute. So diffusion in solid phase is normally tend to be avoided. Here is the bulk movement, which is of more importance in solid, whereas for diffusion in gases and liquid is comparatively easy. That is because of the diffusion coefficient and the factors affecting that. So this will be studied. So first, try to understand the solid-solid category. We have two different unit operations. Either you want solid mixture, which is of different particle sizes, to be separated depending on the particle size. That would be the sieving operation. Or you want a solid of bigger particle size to be grinded to a smaller particle size mixture. So grinding and sieving, the unit operations. With respect to diffusion, the diffusion rate in solids is typically very low. So it's the bulk movement which becomes important over here compared to the diffusion.